Welcome back, and in this video we're going to look at the second section of the electron structure notes, and we're going to be concerning ourselves with ionization energies. So again, you're going to need your notes, and if you could have a periodic table, that would also be handy. So we're on page 14 of the notes, and we're looking at the section 2, which is ionization energies. So if an atom loses an electron, it is said to be ionized, and you need the formal definition of ionization energies. So ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Now, there are a few things to be careful of here. First of all, it is energy required. In other words, it takes energy to do this process. Secondly, we deal with 1 mole of electrons. And lastly, the atoms need to be gaseous. So it's very important that you can write out these equations. So for example, the first ionization energy of sodium, well, we're going to take sodium gaseous, remember? So we do need the state symbols on there, G, and we're going to remove an electron. So that electron has now come loose, and we're left with a sodium 1 plus ion, and it is still gaseous. The second ionization energy of sodium is the energy required to remove the second mole of electrons. So in this case, we're going to start with our sodium 1 plus gaseous ion, and we're going to remove another mole of electrons to leave us with a sodium 2 plus gaseous ion. Notice this is an endothermic process. We can tell this because of these positive numbers here. This is telling me this is endothermic. And all ionization energies will always have positive values. So how many ionization energies can an element have? This is a bit of a trick question. It can have as many ionization energies as it has electrons to remove. So basically it's the same as the atomic number. Do notice these are all free gaseous atoms, not molecules. So hydrogen is not H2 in this case, it is just H. So the amount of energy you need to ionize an atom or an ion will depend on 3 factors. First of all, the number of protons in the nucleus, then the shielding, and lastly, the position of the electron being lost. That's a little bit more complicated because it can involve distance, which shell they're in, which subshell they're in, or whether the electrons are paired or not. So we're going to think about each of these in turn. So first of all, how the proton number affects the ionization energies. Well, this first one is quite straightforward because the proton number gives you the number of protons in the nucleus with the positive charge, and they're attracting the electrons. So an increase in proton number causes an increase in the ionization energies. So the more protons you have in the nucleus, the harder it is to remove that outer shell electron. So shielding shields the outer shell electron that you're trying to remove from the nucleus. So an increase in the shielding will cause a decrease in the ionization energy because the nucleus can't exert such a force on the outer shell electron because the electron is being shielded from experiencing that full force by complete inner shells. Sometimes also this works with subshells. So the last thing we need to think about is the position of the electron. So distance is the first one we're going to look at. So as the distance between the nucleus and the electron being removed increases, ionization energy decreases. In other words, the further the electron is away from the nucleus, away from that positive charge, the less energy is needed to remove it. So shell and distance are strongly related because the higher the shell number, the further the electron is away from the nucleus. So if the electrons are in the same shell, they will have similar ionization energies. This is partly because the shielding remains roughly constant. Next, subshell. You saw in the previous videos that we can divide our shells up into subshells, and those subshells fill from lower energy to higher energy. Now in terms of the P and the S subshells, P subshells are higher in energy than the S subshells, making the P electrons slightly easier to remove. The P electrons can also be shielded by the full S subshell, and again that makes it easier for them to be removed. Lastly, there's the paired effect. Electrons that are paired repel each other. Remember, they both have negative charges, and negative charges repel each other. The only way I can get electrons to share an orbital is to have them in opposite spins, but even then they'll still repel each other. So because there is repulsion between electrons in orbitals, they're slightly easier to remove than unpaired electrons. So now we're going to look at how we can apply these ideas to the ionization energy down a group. So we're going to look at 3 groups on the periodic table. We're looking at nitrogen, going down nitrogen's group, oxygen, and the halogens going down this group. And you should see in all 3 cases, and this is the case for any group in the periodic table, the ionization energy decreases. In other words, it requires less energy to remove an electron from further down a group than it does at the top of the group. So as you go down the group, the ionization energy decreases. So we need to think about this in terms of our 3 main categories: proton number, shielding, and then the position of the electron. So the proton number will be pulling it the wrong way, because as you go down a group, the proton number increases. But this increase in proton number is offset by the changes in the other 2. So even though that proton number is increasing, because the electron being removed each time is 1 shell further from the nucleus, and also it's being removed from a higher energy shell. Remember, you get higher in energy the further you get away from the nucleus. It also experiences more shielding. Those inner shells shield the outer shell electron from the nucleus. So overall, the electron being removed experiences less force of attraction to the nucleus, and therefore less energy needed to remove it. So on page 17, there's a typical exam question explaining the trend in the values of the ionization energies for the group containing sulfur. So we know that the first ionization energy decreases. So we're going to explain that decrease. So I'd like you to pause the video at this point and have a go at writing in your exam answer for that. I would draw your attention to the fact that this answer is worth 3 marks. So you need 3 nice, clear bullet points. And we've been nice to you because we've given you the answer at the bottom of the page. So please be aware that these 3 points could be applied to any group. So the first ionization energy decreases down the group because although the number of protons is increasing, and it is important to say that because you have to explain why the increase in proton number does not cause an increase in the ionization energy. It's because this increase in proton number is being offset by the other 2. So the electron being removed is 1 shell of electrons further away from the nucleus. It also experiences more shielding from the nucleus. So those 2 factors together offset the increase in the proton number, meaning the electrostatic attraction between the outer shell electron or the electron being removed and the nucleus is less as you go down the group. Now you can use this answer for whatever group you're looking at, whether it's group 1, group 7 or group 8. It doesn't matter the group because the argument is always the same. But you do need to consider all 3 aspects: proton number, distance or the position of the electron, and shielding. So that's dealing with what happens as you go down a group. We now need to think about what happens as you go across a period. So we're looking at the bottom of page 18 at the moment, and you should see that as we go across a period, so for example from lithium to neon, there is a general increase. And again, we're looking at the same 3 things to explain why there is a general increase. So again, it's the same 3 arguments. So the proton number is increasing across a period, but the electron is being removed from the same principal quantum shell, so it experiences similar shielding. Overall, that makes the electrostatic attraction between the electron being removed and the nucleus stronger. So proton number is increasing, making it harder to remove. The electron is in the same principal quantum shell, so in this case it's all in principal quantum shell 2, so they've got similar shielding. So overall there's a general increase. One thing also to notice is the size of the atom decreases as you go across a period. So the atoms actually get smaller because you're adding an electron to the same principal quantum shell each time. However, unlike the nice periodic pattern going down a group where they always decrease, here you've got a few blips. So there is a blip here between beryllium and boron. So boron has a lower first ionization energy than beryllium. And here between nitrogen and oxygen. Oxygen has a lower first ionization energy than nitrogen. So there must be special reasons why these two cases exist. So for these two special cases, there are different reasons why the ionization energy does a bit of a dip, does a bit of a decrease. So let's look at the electron configurations of both beryllium and boron. So beryllium has 1s2 and then it has 2s2. So it has 4 electrons in total, 2 in the 1s and 2 in the 2s. Whereas boron is 1s2, 2s2, 2p1. So this comes down to the position of the electron. So even though there are more protons in the nucleus of boron than there are of beryllium, the boron electron, or the electron being removed from boron, is being removed from a 2p subshell. That's higher in energy than the 2s subshell, and it is shielded by the 2s subshell. So that increase in shielding and the fact that it's being removed from a higher energy level means that it requires less energy to remove it. Be very careful that you don't say that the atom is bigger, because actually remember, as you go across a period, the atoms get smaller. So boron is actually a smaller atom than beryllium. In other words, boron's outer shell electron is closer to the nucleus than beryllium's outer shell electron. So it's not to do with that, it's to do with the shielding effect of the 2s and also the fact that it's being removed from a 2p subshell, which is slightly higher in energy. To explain what's going on between nitrogen and oxygen, we again need to look at the electron configuration. So nitrogen has 2 electrons in the 1s, 2 electrons in the 2s, and then has 1, 2, 3 electrons in its 2p. Oxygen, again, 2 electrons, 1, 2, 3, 4. And it's that 4th electron that is important, because here oxygen has a paired electron. And as we looked at earlier, paired electrons are slightly easier to remove than unpaired electrons because there is electron-electron repulsion. So because the oxygen loses this paired electron from a 2p orbital, whereas nitrogen needs to lose the electron from a singularly occupied orbital. And that repulsion between the paired electrons means it's slightly easier to remove the electron in oxygen compared to nitrogen. So on page 20, there's some exam practice. So have a go at those questions. They're all taken from recent exam papers. So pause the video at this point and have a go at those questions. So it's very similar to the work we've just been doing. So why is there a general increase across the period as you're going across period 2? Well, again, the argument is the same as before. The number of protons is increasing. However, the outer shell electron is in the same principal quantum shell with similar shielding. Therefore, you just get a pure increase in attraction. Sulfur is lower than that of chlorine because although the outermost electrons are in the same principal quantum shell, so they have similar shielding, sulfur has less protons than chlorine, or you could say that chlorine has more protons than sulfur. It doesn't really matter, and therefore this changes the attraction and either lowers or raises the ionization energy. Sulfur compared to phosphorus, well, sulfur has a paired electron in one of its 3p orbitals. Phosphorus's 3p electrons are all unpaired. This repulsion between paired electrons means that it's easier to remove the electron in sulfur than it is in phosphorus. So again, a nice little exam question on page 21, asking you to sketch the first ionization energies of period 3 elements. Now try to do this without looking back, and pause the video at this point and then I'll go through it. Okay, So we've got sodium, and then we've got magnesium, and then we're going to drop to aluminium. So the first ionization of aluminium is just slightly lower than that of magnesium. That's because the electrons in aluminium's outer shell are in the 3p subshell, and they're being slightly shielded by the electrons in the 3s subshell. But notice this is only a minor effect, and it's certainly not enough to offset this increase in the proton number from sodium. So aluminium lies somewhere between sodium and magnesium. So then we go up again with silicon, and this time it's going to be higher than either magnesium or aluminium because I've got an increase in proton number again. Phosphorus again higher than silicon. Now we get to sulfur. Sulfur is where we get the first of our paired electrons. So again, that paired electron means that it's just slightly lower than phosphorus, but still higher than silicon. It's not a major effect, it's only a minor effect, it's a blip, if you like. I go up again to chlorine. Chlorine again should be above phosphorus and sulfur. And last but not least, at the end, we have argon, ready for the big drop back as we finish this period. So again, very similar arguments. The pattern across the period, there's a general increase because the proton number increases, but we've got the same principal quantum shell, so similar amount of shielding, so the electrostatic attraction is increasing. The two blips are between magnesium and aluminium and between phosphorus and sulfur. Magnesium to aluminium is due to the fact that you're moving an electron from a 3p rather than 3s, and it's shielded. The dip between phosphorus and sulfur is the paired effect. Sulfur has paired electrons, phosphorus doesn't, and it's easy to remove the paired electron than it is the unpaired electron. And it's these blips that give us evidence for the existence of the subshells, or some of the evidence for the existence of subshells. Because of the blip between magnesium and aluminium, we know that the aluminium electron is being removed from a slightly higher energy subshell. So in other words, all the orbitals in the principal quantum shell 3 are not all the same energy level. If they were, we would just see a steady increase across the period. Likewise, we know that there are paired electrons, and it's easier to remove that paired electron, and that explains the discontinuity between phosphorus and sulfur. The last thing we should notice, especially about these graphs, is this big drop here between neon and sodium, between helium and lithium. So here we have to remember we're changing whole principal quantum shells. So the electron being removed from helium is a 1s electron, and the electron being removed from a lithium is a 2s electron. So it's got a full inner shell of electrons shielding it. It's much further from the nucleus because it's the whole principal quantum shell further out, so it's much, much easier to remove. Likewise, the same here. Neon, the last electron being removed from neon, is being removed from a 2p subshell, whereas sodium, it's a 3s subshell. Again, a whole principal quantum shell further away from the nucleus and a whole level of shielding. So it's far easier to remove sodium's outer shell electron compared to neon. Please don't revert to a GCSE model of talking about full outer shells. Those really shouldn't be mentioned. The three things you need to think about is proton number, shielding, and the position of the electron.